Hi, my name is Rodrigo Aldana. Today I will be talking about this number. Let me warn you that this is not an interesting number by itself. Note that it is neither a prime number nor a fundamental constant for any interesting problem. However, I'm talking about it since it is used as a tool by the real protagonist of this video. And it is interesting since in this context, this number is a magic number. The real protagonist is this little piece of code, which I copied exactly, even with the original comments. It is known as the legendary fast inverse square root hack, which is supposed to compute the inverse of the square root of a floating point number. It was supposed to be part of the video game Quake 3 Arena, and there are a lot of names related to the authorship of this piece of code, but let's not focus on that. Take a look at the code. It is written in C, so for anyone not familiarized with this language, this code might already seem like some sort of spell. However, if I show this code to the most experienced engineer, there is one line of code that will still surprise him, and this one. And that's because the code is operating with this constant. This constant is represented in base 16 or hexadecimal. If we write it in base 10, we arrive at the magic number at the beginning of the video. And somehow this number is related to computing the inverse of the square root of any floating point number. Even the most experienced engineer would say that this is magic. And that's because in software development we say that we used a magic number. This is a constant that appears explicitly in the code, and there is no explanation on why it's there. And sometimes, if we change it a little bit, everything might stop working. So, the purpose of this video is to explain this mystery. Let me start with some motivation. Why do we need to compute the inverse of the square root in the first place? Actually, there are a lot of places in which this operation appears, ranging from signal processing, robotics, and computer graphics. But let me focus on this particular example. Suppose we wanted to generate this image. We have a virtual environment and we want to show how light emitted from a source gets reflected over some mirror-like surfaces and then reach the perspective of the camera. A very simplified procedure to do so would be the following. Picture a light source emitting this ray of light over a mirror surface. To know how light will be reflected, we take a tangent plane over the surface which is characterized by a normal vector, which is orthogonal to the plane. Then, the light will be reflected along the axis of the normal vector. In particular, the angle between the incident light and the normal vector is the same as the angle between the reflected light and the normal vector. So, everything reduces to computing such angle. If the incident light direction is represented by the vector u, we know that the dot product between these two vectors is related to the magnitude of them and the cosine of the angle between them. So, we can obtain the expression of the angle. Note that in such expression we need to compute the dot product of the normalized vectors, this is, divided by their magnitudes. If we put a reference system, the vectors can be written in terms of their components, so the magnitude is written as follows. Hence, to compute the normalized vector, we have to multiply with the inverse square root of ux squared plus uy squared plus uz squared. And well, we need to do that for this point, but also for this one, and this one, and this one, and all the points on the surface. So, if we want to end up with a good quality image, we have to make the operations thousands of times. And in a video game, for example, that happens many times per second. So it would be nice to have an efficient way to compute the inverse of the square root fast. How would you compute such operation normally? Well, some may say that they would import their favorite math library and just call the square root function. And that's fine, but that's not the question here. We want to understand what's inside, say, the square root function, and devise a way to improve its speed. One way is to use the Newton-Raphson method. This method finds a number x star which is a solution of f of x star equals 0. This is, x star is a root of f. The method looks something like this. We have our function f and we want to find this point x star. We start by an initial guess, which may be a bad guess of what x start is. Then we compute the value of f, and we perform a linear approximation of f at this point. This is the tangent line here. Then we obtain the zero crossing of this line instead. Hopefully, this will be a better guess of x star than our initial guess, so we perform the same procedure again, until we are close enough to the real solution. The explicit form of this algorithm is written as follows. So, the Newton-Raphson method basically is, we start with an initial guess and repeat this iteration. We know that under some conditions on the initial guess and the function f, our method will converge to x star, as the number of iterations go to infinity. However, we can't afford infinite iterations. Instead, we want to iterate until we are close enough to the solution. We can measure how close we are to convergence by, for example, the absolute error, which is the error between the real solution and our approximation after n iterations. Note that we can't compute this quantity since we don't know x star. Another option is a relative error, which is the error between two consecutive iterations. Hopefully, as the algorithm advances and we start converging, these errors will become smaller. Then, a typical stop criterion would be to iterate until this relative error is less than some small number. But what does this have to do with the inverse of the square root? Suppose we want to find x, which is the inverse of the square root of m. Then, after some algebra, we can arrive at this expression, which does not involve any square root and is of the form of the problem we were talking before. Now, we can apply Newton-Raphson to find the inverse of the square root as follows. With this expression of f and its derivative, we can plug that into the Newton-Raphson method. After some more algebra, we get this nice expression. Note that it just involves some simple additions and multiplications. Then, the algorithm for the inverse square root would be something like: first, find an initial guess, then repeat the Newton-Raphson iteration until the relative error is small enough. This is an example in which I computed an approximation of the inverse square root for numbers between 0.1 and 10. The initial guess is 1 over m instead of the inverse of the square root of m, which seems reasonable, and an epsilon of 0.02. In the first figure, I am showing in red our approximation, and in blue a better approximation computed using a standard math library. The second figure shows the absolute error. A more interesting figure is this one, which shows how many iterations we needed for the method to reach our stop criterion. In some cases, only one iteration was needed, and in others up to 11. That's because the better the initial guess, the faster the method. So, improving the speed of this method means to obtain a better initial guess, and then refine that guess with a small number of iterations using Newton-Raphson. Then, what is a good but fast approximation of the inverse of the square root? This is related to our magic number. To explain the hack, let me first explain a little bit of how numbers are represented in computers. Take this number. We say that this number is in base 10, since each digit represents a different power of 10. We can always factor out the greatest power of 10 to write the number as follows. We say this number is written in scientific notation, in base 10. However, we can perform the same in base 2, or in binary. Here, the powers of 10 are replaced by powers of 2. This is, a fractional number can be represented with a 1, followed by a point, followed by a string of binary digits called the significand or mantissa, each representing a different negative power of 2. Finally, everything is multiplied by 2 to the power to some exponent, which might be negative as well. This is called the floating point representation, and by standard, all computers support such representation. Take for example the single precision float of 32 bits. We use a bit for the sign, then 8 bits to represent the exponent, where we store not the exponent itself, but the exponent plus a bias of 127. Note that any exponent written as a signed integer in 8 bits might range from -127 to 127, so we add 127 to store just a positive number. And finally, we store the mantissa, which is the string of bits representing negative powers of 2, in 23 bits. At the end, the number represented in floating point is -1 to the power of s. This is positive if s is 0 and negative if s is 1. Next, we multiply by 1 plus r, which represents the string of bits we saw before. Remember, we always have a 1 at the beginning of the string of bits, so this string of bits can be represented as 1 plus 0 point the string of bits in the mantissa, and we write this as little r, which is a number between 0 and 1. Finally, 2 to the power of the biased exponent minus the bias, which is the original exponent. Now let's see how this fits into our original problem. If we wanted to compute the inverse of the square root like this, we can take the base 2 log of both sides and apply some properties of the logarithms to obtain this expression. But remember that the numbers x and m will be represented as positive floating point numbers, with their mantissa and exponent. Then, if we take the base 2 log of x, we can use the log properties again to obtain that it is only necessary to compute the log of 1 plus the mantissa, and then just add the exponent. Now, here's the trick. I'm plotting log of 1 plus r, where r is any number between 0 and 1. Now, how close this function is to r itself? In fact, this approximation is exact on both ends. However, is somewhat inaccurate in the middle of the interval. Then, we may think in a different linear approximation of log of 1 plus r by adding a constant, such that the maximum error is reduced. Here I am plotting the maximum error we get when choosing a particular value of sigma, and we can see that there is a minimum value which is exactly 0.04343 for sigma. Thus, we can approximate base 2 log of 1 plus the mantissa by a linear function of the mantissa. Therefore, we have a linear approximation of log 2 of x by adding the exponent 2. This is nice, but we haven't obtained a way to compute the inverse of the square root yet. The other piece of the hack is to think of the 32 bits of the floating point representation not as a float, but as a 32-bit integer. This is to reinterpret the floating point value as an integer. We can start by saying that this number is positive, so that the sign bit won't matter. Moreover, remember that the mantissa represented a series of negative powers of 2. If we interpret that as an integer, those bits will represent the first 23 positive powers of 2, represented here by capital R. And this number is related to little r by a factor of 2 to the power of 23. So the integer stored in this variable will be at least this value of capital R, plus the contribution of the exponent. Note that the exponent bits lay in the place of powers of 2 greater than 23. Then, we have the exponent plus the bias times 2 to the power of 23. Rearranging this taking into account that capital R was little r to the power of 23, we get this expression. In summary, given a floating point number, we have a way to reinterpret that register as an integer, but also we can always reinterpret that integer as a floating point number again. Using this fact, we will stick our base 2 log approximation as follows. Note that we can add and subtract sigma in the integer representation, such that we have the form of the base 2 log approximation we derived before. Therefore, the reinterpretation of the integer can be approximated in terms of the base 2 log of the original number x plus a constant, and we can do the same for m. Then, the complete method to compute the inverse of the square root approximation is the following. First, we reinterpret m as an integer. Then, we use that integer to approximate the integer representation of x. And finally, we reinterpret the integer as a floating point representation to obtain our result. The trick lies in the step 2. We can use the relation between the log 2 of both numbers we saw before and write ix in terms of base 2 log of m. Rearranging a little bit makes evident that this term can be obtained in terms of im as follows, getting rid of the logarithm. Finally, rearranging a little bit more, we obtain this expression. We have a constant value which depends on the bias of the 32-bit floating point standard, which is just 127, the value of sigma used to approximate the logarithm, and we subtract half of the integer representation of m. If we use sigma equal to 0.04343, which was the optimal value for the base 2 log approximation, this constant, rounded to an integer, equals to this big number, which is not quite our magic number yet. The fact is that the best choice is not to use the sigma value to best approximate the base 2 log, but the best sigma value to approximate the final result of the inverse square root. In some sense, the best sigma value to approximate the inverse square root, using this method for the initial guess, and only one iteration of Newton-Raphson, which results in this value of sigma, which results also in the magic number we were interested in. I will leave some documents in the video description for a more formal analysis on how this optimization procedure is performed. Then our approximation looks like this, and we can finally read the code making sense of it. There is our magic number in base 10. This line of code assigns the number m, which we want to take the inverse of the square root, to this variable, and use pointers to obtain the integer representation of the floating point value m. Quickly explained, the ampersand operator takes the address of y, which is a float, and then we make a casting to convert this pointer to a float to a pointer to an integer. Then read the content of that address as an integer and not as a float. In the next line, we shift the bits of im one time to the right. This means the following. Note that by shifting, we'll lose the least significant bit. Also, both integers are a power series of 2, which are directly related since the one on the left is exactly the one on the right, but divided by 2, without the fractional terms. Then, this piece of code just divides by 2, so this whole line of code is our approximation of the square root. Finally, we reinterpret the resulting integer as a float, using the pointer trick just as before. Now, suppose we ended our function here, to see how good this initial guess is. Note that the results shown in red resemble very good the real value of the inverse square root, shown in blue. But the absolute error is still big. Finally, we perform always just a single iteration of the Newton-Raphson to refine the result, where a second iteration was apparently part of the code, but was commented in the final version. Note that the results improve a lot. Now that we understand the code, we ask, is this a good piece of code? Well, it represents a very clever approximation which outperforms the typical solution speed. However, without all this explanation, this approximation seems arbitrary and lacks of motivation just by reading the code. I repeat again, the approximation seems arbitrary and lacks of motivation if no further explanation is provided. Let me take this opportunity to comment on the following internet phenomenon. Many mathematicians, physicists, and engineers themselves post many memes like these ones. Most of them are about how engineers approximate. Although I understand that these are all meant to be jokes, they hide something which I want to discuss. Is approximating something bad? Me, as an engineer, I claim that approximations are useful, and most important, many times approximations are necessary. Actually, I don't know any engineer that truly believes that sin of x equals x. However, I know a lot of people that believe the following, even though this is just another approximation too. The important thing is that we can always make an approximation in order to go beyond the technical difficulties of the original problem, in order to obtain intuition or to directly innovate from there. At the end, we can always propose a solution and then test if that idea, solution, or approximation fits the requirements of the problem we were working on. And if that approximation was just bad, we can always go back and improve it. And whenever we communicate solutions by teaching or just by coding, it is important to always motivate what are the design decisions that were made in order to arrive at that solution. Throughout an engineering bachelor, there are many approximations, algorithms, or techniques that might seem arbitrary for a student. However, the fact is that most of them make perfect sense once you understand what is the motivation that led to them. And as John Cook wrote some days ago on Twitter, when you see a clever algorithm presented in a computer science class in 20 minutes, it can be intimidating. You reasonably think, I could never come up with anything like that. But the person who did come up with it spent more than 20 minutes thinking about it, maybe months or years. They were motivated by some problem to come up with the algorithm. They may have been driven to the solution by long experience that cannot be duplicated in classroom. You may learn about the algorithm in Bacon, but they did not. For me, it's very interesting to learn a new technique. But I believe it's also important to learn a little bit on the original motivation and decisions that led to that technique too, since those may be useful for other problems. And well, that's it. Thank you for watching.